A very good evening and happy Dasera. Welcome to week 11 of doubt clearing session on fundamentals of additive manufacturing. Let's start today's class. Yes. So if you remember, we have already gone through the laser-based powder fed additive manufacturing process, that is basically directed energy deposition DED. It was powder fed, it was wire fed. So wire DD, powder DD, we are done with. We have also learned about the electron beam DD with wire. Electron beam systems are often used in vacuum, so powder based is not possible. So wire based electron beam aim is covered. So the remaining only the last option we have is the powder bed fusion process, which is the last state of the art or second last state of the art in my classification tree of additive manufacturing. In powder bed fusion, we have two type of powder bed fusion, whether it's SLM or it's SLS, means it's selective laser melting or selective laser sintering. Now, as an energy source, I have mentioned laser, but electron beams can also be used. So EB, PBF is also there. So PBF, powder bed fusion, can be again of two types, PBF EB, electron beam, or PBF LB, laser beam. In this class mainly will focus on to the PBF LB, that is powder bed fusion with laser beam. As the name suggests, powder bed fusion. So there will be a bed which is also known as the substrate onto which we print, and on the substrate the powders are spread. So that's why it's called a powder bed. So let's go to the slides one by one. So here it says that if I in a broader way, if I classify the AM process, then its powder-based AM can be classified into two groups. One is powder-fed. Just a second. One is powder-fed. That is this PBF. And another one is, powder-fed, that is DD. And PBF is the powder bed. Powder-fed means we have a nozzle. And through the nozzle, my powders will come, and through the central sort my laser will come. So this is my laser and this is my powder. So all my powder and laser will interact over the build plate. This is my build plate. And the deposition will take place here. This is my deposited bead. But in case of powder bed, the scenario is little different. Powder bed means nothing but a substrate, which is the build plate. Onto the build plate, my one layer of powder will be spread. Spread by how? Spread by a recoater. A recoater is nothing but a blade or a roller or some mechanism through which you can finely and uniformly spread one layer of fine or thin powder layer onto the build plate. So this is my powder bed. So I have two processes, powder fit and powder bed. Then in powder bed, we have binder based powder bed. We have energy based powder bed. So binder based means that the powder that was spread onto the build plate is mixed with some binder, or the powder is spread and from the top of the head, from the nozzle, the binder is coming. If this is my top view and my binder is coming like this, so this is the portion where my binder has fall onto. So this is my part. The powders are getting binded together because of the adhesive in that zone. So my part will be made on that zone, and in the other rest of the part of the build plate, the loose powder will be present as it is. So that is the binder based. Energy based means if this is again the top view of the powder bed and the powder is spread over the build plate, and the energy beam will scan like this and solidify, melt and solidify the part that you want to make. So now this is the part which has been made using the energy beam. The energy beam can be laser. The energy beam can be electron beam, EB. Then in energy beam, as I said, now in laser, we have two processes: selective laser sintering, selective laser melting. Melting means complete.
Ma'am, what is the full form of PBP?
What is the full form of?
Like, energy beam based powder bed, that short form is
EB is
PBP.
electron beam.
PBP.
Yes. PBF is powder bed fusion.
No, before that on the top it is PBP, right?
No, no, it's PBF. I
Okay.
only wrote it last year. Yeah, it's PBF. So PBF, one is a laser beam based, one is energy beam based. Then SLS and SLM. So SLS means the process is same. In SLS, it's sintering mainly at the region of interest. The powders will get fused together. Like if these are the two powder particles I have, they will get fused together because of the pressure and the heat, but they will not get melted. But in melting, these are two powder particles, those will get fully melted together. And this is the melt pool, and out of the melt pool, you get the solidified. Like after melting, there is solidification. But in sintering, it's the fusion of two powder particles, not melting. So these are the two processes we have. So this is the overall chart or classification tree of powder bed fusion type of additive manufacturing process. Then, if I start with the history, then from 1971, this process came. This process came, and it's not very old, but the process was not that much useful at that time because there were very few companies who started it. EOS is one of the leading company in this machine or making this machine. EOS electro optical system, this is a company name which first introduced us with PBF systems. There is another company called SLM. The company name itself is SLM as well. So SLM also introduced us with PBF system. So these are a few other pioneer companies, 3D System Corp, DTM, etc. EOS is the most common, mostly used, and very standard machine. So when you talk about additive manufacturing and using additive manufacturing in the real applications, like where we can use additive in the electronics for making very small chips or metal parts. Thus, recently Apple has introduced us that they have launched their very new watch series in which the case itself is 3D printed. So they are using 3D printing for small part manufacturing. Then we have a bigger sector like aerospace, NASA or ISRO. They are also making parts out of additive manufacturing. So when you're talking about this company applications, you have to be very serious about the standard. Company will always want to use a standard machine rather than any normal company machines. Because when I'm saying the word standard, that means the process parameters for the normal, very common materials like aluminum, stainless steel, copper, titanium, Inconel, these are optimized by the company. And when you use this optimized parameters to print this metal parts again and again, you get the same repeatability and reproducibility. So standard means they are following a standard, that is the ASTM standard for additive manufacturing. And wherever your machine is in Europe, your machine is in India, or your machine is in Russia, your same process parameter will be used for the same powders, no matter from where you're buying the powder. If your powder has that same composition and size distribution, then your part should have the same quality. Quality means first is the density. So your part will have 99.9% density that EOS offers, often for various metal. And then your part will have that tensile strength, that hardness, that toughness, ductility, strength, I already said, all the properties. Okay. So when I use the word standard, that means it has a very good reproducibility and repeatability, which is very much needed, because it may happen that I'm doing the research at IIT Delhi in India, and that part will be used by US government. So if I am giving them the data should be reproducible for them and for their powder and their environment as well, because environment has a huge effect on the 3D printing process. So that's why these standard things come. So EOS has set the standard. So they have the standard, they have the protocol, they have their powder, their machine, their process parameters, like parameter values, everything, and part quality. They also tell you that if you are, it's not for EOS, it's for any company like SLM, EOS, or 3D system. If you are buying their machine, they will tell you that if you are processing this powder with this much process parameter, then this will be the yield strength you can expect. This will be the grain structure. This will be the microstructure, hardness, phases, and everything if you're printing the part with our process parameter. So in that case, these two companies are the leading companies. Then there are other companies as well who are also selling LPBF systems. Now, one problem I would say with LPBF is it's very costly machine. It's a very costly machine, and the cost of the powder is already higher because it's powder. We are making powder out of the raw materials, wire or tubes, or just bulk material. You are making powder. So we use powder atomizer. We use powder atomizer to make the powder. To make metal powders. You can search for atomizer, you will see the principle. So it's very simple. There are plasma atomizer, there are gas atomizers. So you make the metal powders. Then, so one most important reason being that my powder has to be spherical. My powder has to be spherical with a proper range in the distribution. So for PBF, it's mostly 15 to 45 micrometer, the powder particle size distribution. So I need a perfect distribution of the powder. The powder particle size distribution. So it should look like Gaussian. This is the 45, 70. And this is the 15. So 15 to 45. and this will be around 33 micrometer number of particles. So this is the distribution curve. So the distribution curve will look like this. The distribution of this 15 to 45 will be Gaussian distribution. The powder should be spherical in size. So these are the specific need we have for the powder to be used for PBF or DD. For DD, the particle size distribution will be a little higher than PBF, but it's same spherical and Gaussian distribution DD. So we use the powder atomizer. Then the machine itself is very costly. So as the machine is costly, the printing is very costly. So these days, people are trying to make their own homemade PBF systems to minimize the cost so that they can get the benefit of PBF over DED, but at a lower price. So this is the state right now. Then comes to the working principle. So for working principle, it's there will be a powder dispenser. This is a powder dispenser where we put the powder first before starting the machine. After putting the powder, this is the build plate. This is my substrate. If you see, this is my substrate. So substrate is mounted on a different CNC. Now the substrate goes down and this dispenser moves up. This recorder spread that extra powder, that extra level onto the build plate. How it works, I have a video for that. So can you see this GIF? So see, this is the powder dispenser moves up and this is the recorder that spreads the powder onto the build plate. Now this is the build plate. Okay, this middle one is the build plate that goes down and you get the printed part because this is the laser which is coming. This red laser you see, this is the laser that is coming. And this is the galvo scanner. So this is F theta lens. This is galvo scanner and you get the laser because of the motion of the galvo scanner onto the build plate. Now, what is this third region? First is the dispenser. Second is the build plate. Third is the collector. So when you are spreading the powder, obviously there will be some extra powder and that extra powder will be collected in the collector. Later on, you can sieve the powder and reuse it. So this is the overall process. Is it clear?
So when laser falls onto the powder bed, what will
So
happen then?
the laser falls over the powder bed because this is a substrate. So on the substrate, the part will be made. So the laser is subsequently melting and solidifying each layer. So this is not only one layer thing. There will be hundreds, 500s or thousands of layers. This is the mechanism how each layer will be spread. This is the video where first layer is spread. But when you repeat this process 500 times, then you get the whole part. And when you are spreading the second layer, also first layer of powder will be present here. So right now it's empty, but when you will be spreading the second layer, the first layer will be presented here. So this is the overall mechanism. Okay. Any more doubt? No.
No.
Okay. So now let's understand how the process works for PBF LB. So previously it used to be called as LPBF, but recently the name got changed to PBF LB to standardize the PBF process with laser beam or electron beam. So PBF LB or PBF EB. So it's PBF LB. Now this PBF LB will have different material delivery system. laser delivery system, the manipulator, and the laser source. Also, one extra part in PBF we have that is called the filter. So I'll be talking about all these topics today. So first is the material delivery system. This is done by recoater. Recoater is nothing but we have a build plate. As you have seen on the build plate, this will be a recoater with a blade, and the powder will be spread by the recoater onto the build plate. When the recoater moves from one side to another side, when the recoater will finally reach this portion, my powder will be spread all over the build plate. And the powder thickness is generally from like 10 to 100 micrometer or 20 to 100 micrometer. Generally, we use 20 to 60. But if you want to scale up the process in terms of time, if you want to print faster, then you can go for 60 to 100 micrometer layer thickness. How to get the layer thickness? So basically, the distance between the build plate and the recoater blade, if this is the distance between the build plate and the recoater blade, then this is the layer thickness in micrometer. So this is how the material is delivered, but this is happening at the time of process. But when you have not started the process, that time we supply the powder here. So we basically put the powder, pour the powder after sieving. Sieving is always very important, whether it's new powder, virgin powder or not. But sieving is important just to avoid any further environmental contamination of the powder. So we sieve the powder and we put the powder in the container, in the dispenser. And from the dispenser, the powder comes. This is the dispenser and the powder comes from the dispenser to the bin. So that is the material delivery system here using the recoater or the roller. The PBF is completely different than DD. So that's why you have to understand the difference between PBF and DD. In DD, we were using the powder hopper. The powder was kept outside the machine in a different machinery component, which is called the powder hopper. And from the powder hopper, the powder was coming through the pipes. So as it was coming with the help of carrier gas as argon, nitrogen, to the cladding head using some pipes. That's why the powder distribution was quite higher. It was 45 to 120 micrometer. Whereas in PBF, we are using 15 to 45 micrometers. So then our material delivery system is done. Then we have the laser delivery system. So in this video, it's shown that this is the source. This is the F theta lens. And this is the galvo scanner. So source is there to produce the laser. F theta lens is there to make the laser in a focused point till here to here and here to here. So this is my zone of interest, or this is my build plate volume, you can say. Area, you can say build area. This is my build area. So my build plate goes down. So therefore, my laser doesn't go down. The laser will always be focused at this plane. But it has to be focused from this position to this position, which is the extreme end in the X minus and X plus. And it has to be focused in this and this direction as well, which is the extreme Y minus, Y plus and Y minus. so that my energy density will be fixed for a given energy or for a given laser power throughout the bill. That's why we use F theta lens. F theta lens's work is to make the laser focused at a particular area, at a given area. Understood. Now the use of galvo scanner is similar that what we have used for VAT photopolymerization. So galvo scanner is rotating at this direction and this direction. It's basically tilting in X and Y direction. It's tilting in X direction, it's tilting in Y direction. Why? So to move the laser beam on top of the bill plate. Because the galvo scanner is fixed. Sometimes it's making the laser fall on this point. Sometimes it's making the laser fall on this point. Sometimes it's making the laser fall on this. Sometimes on this. Sometimes on this. So it's moving the laser beam on top of the build plate very fast, very rapidly. So that rapid motion of the laser on top of the build plate is not easy task. Is it's absolutely not an easy task. So that's why galvo scanner is used, because galvo scanner's working is to make the laser beam move very faster on a given area. In LBBF or in PBFLB, the main advantage here is to make very intrinsic parts, intrinsic components, and with a very lower feature size. That means your part will be very small. Your part can be very small. Your part can have very high resolution. That means a very small features you can easily print in your part. You can easily incorporate into your part and print. That is the main advantage of LPBF over DD. Just note down the points that I'm saying, because you can have questions on this thing. Because these are the most important points and comparison between PBF and DD. So when you are talking about PBF, you have to move the laser very fast. So this question may arise that why I have to use galvo scanner and why not a normal CNC to move the laser? Because in LPBF, it's better to call it as PBFLB. In PBFLB, the scan speed is around 300 to 600 to sometimes 1500 millimeter per second, whereas in DD, this scan speed lies between 300 to 600 millimeter per minute. See the drastic difference. It's 60 times more, 100 times, 200 times more if you see this. So the first reason is clear. So in LPBF, we are moving the laser beam very fast. So CNC cannot be used because there will be vibration in the CNC if you want to move a CNC, a physical system this fast. So that's why an optical lens called galvo scanner is used to move the laser beam. Now, I know the reason why galvo scanner is used, but why this high scan speed is used? That is also important. Can anybody guess why this high scan speed is used? No? So when I'm talking about LPBF, you have to understand what is the utility of scan speed. So scan speed is important to calculate the energy density. However, volumetric energy density is a very vague term, but still I'm using volumetric energy density. That is P by scan speed into spot diameter into the laser thickness, layer thickness. So this is the volumetric energy density that we use to calculate what is needed for melting the metal in case of PBF LP. Now this is my power. This is my spot size. This is my scan speed. This is my layer thickness. I think I made a mistake in this formula. This spot size is not here. Something else is here. Anyway, we can take this equation for the time being. So here I am interested to calculate that how much energy or energy density or volumetric energy density is needed to print a part. Sorry, in this formula, this has to be hat spacing. This is hat spacing. I forgot. Not spot size. Spot size is not in this formula. There is another formula called line energy density. That is having the spot size. That is P by VD. V is the spot size. So when you are calculating the energy density, see if you have 50 grams of powder or 5 grams of powder, to melt 5 grams of powder, you need same energy density for LPBF and for DED. This is true because the powder is same. If you have a stainless steel powder, SS powder, and you have 5 grams of it, then printing it, whether printing it in DED or printing it in PBF, the energy density has to be same. In case of PBF, now if I draw a comparison chart, then in case of PBF, the spot diameter is often as 90 micron or 100 micron or even 60 micron. In case of DD, it's 1.5 to 3 millimeter. So this term has a drastic difference in both the case. Now in case of DD, the power we use is often 1 kilowatt or 2 kilowatt. So as the spot dia is very, very less, so I don't have to have a very high power to get the high energy density. Energy density is basically at this spot how much power is coming. If my power is coming here is 400, but my spot diameter is 3 millimeter, and here my spot diameter is 100 micrometer, and coming the same 400 watt, what do you think? This will have greater power density than this one. This will have very high energy density than this one because it's a small spot. At a small spot, at a very high power is higher energy density. Because of which here we use very less power, 100 to 400 watt, and a very high scan speed. Whereas here we use a high power and very low scan speed. So to match the energy density, to get the energy density necessary, we have this drastic difference between the scan speed of PBF and DD process. So now you've understood why there is this drastic difference between the process parameter values between two additive manufacturing process, whereas both uses better to print parts. So now if I use very high power or very low scan speed in PBF, my laser can actually penetrate and my laser can make a hole instead of melting the metal. My laser can burn the powder, can evaporate the powder. That much high energy density will be there if I'm using very low scan speed. So to match or to get or to achieve that high scan speed, we go for galvo scanner based systems instead of CNC based systems. Next, we have the manipulator. So I hope that material delivery system and laser delivery system is clear by this time. So now we have the next thing called the manipulator. So manipulator is basically how you are handling the tools. So in case of DD, if you remember, we have a cladding head. The cladding head is mounted on a robotic arm or it's mounted in a CNC based system. So this head mounted in a CNC or this head mounted in a robotic arm is the manipulator for DD. But now we are talking about PBF where the system will be fully closed. This is the system fully closed. Here we have dispenser, powder filled. Here we have bill plate, lead screw based. It will move down by 1 layer thickness each step. There is a recoater which is used to spread the powder, and there is a collector where extra powder will be collected. And now on top of this recoater is mounted in a CNC based system. So this recoater will be moved in plus and minus X direction with the help of a CNC. But the laser here is coming through this galvo scanner to the, sorry, here is the build plate. So my laser lens has to be here. And this is how the laser will come here and here and here. So my galvo scanner will be here and my F theta lens will be here and then my source will be here. So this chamber will be fully controlled. Like the chamber will have a very controlled atmosphere, controlled atmospheric pressure. The oxygen will be 0 ppm at the time of printing to minimize or to avoid the oxidation in the printed part. So this is how the PVS system is very expensive, and the manipulator here is the whole all the tools. I will say the manipulator for the energy density. Sorry, for the energy source is the galvanometer based scanner. The manipulator for the build plate is the CNC based system. The manipulator for the recoater blade is also the CNC based system. All the things that other than laser is the CNC based. Only the laser is galvo scanner. So this is the manipulator. So fourth was the laser source. So manipulator is done. Then we have the laser source. Source is we often use the fiber laser. Fiber laser has a greater life than diode laser. Fiber lasers give us a very perfect Gaussian beam as LPBF is used to print parts with high resolution with a small feature size parts. So it's recommended to use a perfect single mode Gaussian beam. That can be done easily from fiber lasers. So in fiber lasers, we don't go for very high laser power. We go for maximum 400 to 500 watt laser, which are low cost as well. And we integrate it with the S theta lens and galvo scanner and get the laser. So laser source is done. Now the most important and unique part in case of TDF is the filter. So let's discuss about that. So as I said, when we print the part in LPBF inside the machine maintains a controlled atmosphere, like as a shielding gas in case of DD. If you remember, we were providing some argon or nitrogen in the working zone. The argon or nitrogen was provided with the help of a pipe or a nozzle. It can be in the nozzle itself, in the cladding head itself, or it can be externally fed argon. Here in PBF, while printing, this whole chamber will be filled with argon gas. Okay, the whole chamber, and the pressure will be maintained. It can be 6 to 9 bar or millibar. I don't remember the exact value, but the pressure will be maintained. The oxygen will be not present, so it can be 0 ppm. The other gases will not be present, so it will be only argon with the constant pressure. Now, how to maintain this constant pressure argon? So you can say, what is the problem? I'll fit a pipe here and bulk pipe. So there will be argon field and the argon is going inside. So it's filled with argon and there is a valve. So it cannot come backwards. So it's only can go in this direction. So the argon is filled, and I will install a pressure gauge here that will show me the pressure. When I see the pressure drop, I will again supply the argon to maintain the constant pressure inside it. Right? It's simple. Then what is the need of the filter? Because it's simple that I supply the argon, I can even make the whole system automated so that my argon will be filled automatically inside the machine. Uh, Whether there is a pressure drop or not, I don't care because the system is automatic. The argon will be filled automatically to maintain that constant pressure. But at the same time, if you think about the process that is going on, that is the melting and solidification, while the laser will melt the powder particles, when the laser is uh, melting the powders, there will be fume from the powder. There will be fume because you are melting metals. There can be fume, there can be carbon because when you overheat something, there can be carbon particles. There can be flying powders as well because powders are very lightweight. You're spreading the powder every time. So there can be some powders in the environment, in the chamber inside as well. So now, previously I was concerned about the argon, but argon maintaining a constant pressure inside the machine of argon is easy. But now we have argon inside it. If we are printing with argon, we can print with using nitrogen as well. Then there is nitrogen at constant pressure. So argon, we have the fume because of melting. We have some carbon or some carbon dioxide is not possible, but carbon is can be some black ashes you can see or ashes you can see. Then we have the powder particles also flying here and there because they are very lightweight. So these all are now mixed in the environment inside the machine. These are not only argon, they have all the things. So if there is present, there are this fume, ashes, powders present after one layer, then after 500 layers, the chamber will be filled with fume only and there will be no argon. And you cannot separate out these things very easily. So what we do instead is there will be a recirculating filter system, RFS. RFS is very important for PVS systems. So there will be a grit nozzle or there can be different type of nozzles with holes that will mainly suck out the fume and the mixed argon, and that mixed thing will go to the filter system, RFS. RFS is having the paper-based filters with a high pressurized argon. So the argon is also going in the RFS. So the RFS will filter out this mixed gases and the excess powder, fume, ashes, everything will be segregated, separated out, and the pure argon will be again delivered in the chamber through the same nozzle. So that's why this RFS will be connected through this argon. So here the argon gas cylinder is connected. Here the RFS is also connected. So the argon is coming from the cylinder, but inside the mixed gases will go to the RFS, and the RFS will filter out, segregate the powders and produce the pure argon here, and they will recirculate this pure argon again inside the machine so that I can save the cost, because if you circulate the argon and just throw away the mixed gases to supply the fresh argon again and again, then this is going to cost a fortune, because when we operate LPBF machines, we print for days. Like the machine will be printing parts for days, for 10 days, for 20 days continuously. If one cylinder is costing around 25 to 30,000 and you are printing for days, you can calculate how much argon is needed. So that is not a solution. And LPBF machines were invented for the mass production in aerospace companies, in very sophisticated companies, in a sophisticated sectors to print resolution, high resolution parts. So if they are printing very high resolution parts for aerospace in NASA or ISRO, they can't afford this type of shitty things basically, because if you are consuming this much argon, there is no point of using this machine for part production. We can go for less costly DD. So that's why, to make it more money efficient, cost efficient, and time efficient, and a better system, this RFS was designed particularly for PDF machines. If you have any doubt, you can ask me in between. So this is the difference, one of the main or major difference we have between DD and PVF. PVF have this RFS system because PVF is operated at a controlled closed door environment, whereas DD is often operated in an open environment. So these are the all important points about LPBF that I wanted to discuss. Now let's go back to my slides. If you have any doubt in between, you can ask me.
And so the argon gas that is supplied will be again recirculated, is it?
Yes, yes. So now this is my dispenser, this is my bill plate, and we have understood this thing. Now the joining mechanism can be of three types. Sintering, liquid phase sintering, and melting. So sintering means if there are these powder particles, these are close enough to join together by fusion of atoms in between. So there can be pores, major pores in the printed part. Liquid phase sintering means not exactly liquid, but they have started softening and liquefying. At that stage, you are sintering the powder. Sintering always have the presence of pressure in it. But in case of melting, it's complete melting, it's complete melt pool formation, and then solidifying the whole thing to get the final part. Then in subsystem, so for the material, it's a little different than DD again. So in DD cannot be worked with polymers. There is no polymer DD present, but we have the polymer PBF. So PBF can be used for making metal and polymer, both the parts. Metal can be used for sintering and melting, both the cases, but for polymer, it's little difficult to melt polymers and then fuse. So sintering will be the better option. So sintering is used for polymers, and melting and sintering both are used for metals. In case of polymers, there are different type of polymers. So there can be coated polymer as well, like metal coated polymer. When you sinter them together, you have the metal inside the printed part. So kind of a metal polymer matrix composite you can get with the metal reinforcement. You can have the same concept used for metal matrix composites as well. So you can have a coated metal powders which are coated with other metals, so that you are not melting them, you are sintering them. So you have the metal matrix composite with different metal reinforcement. Same thing you can do for ceramics as well. So ceramic printing is also popular in case of PBF. You can print ceramic for different application using the same selective laser sintering process. So it says that coated and mixed are the indirect route, whereas the mixed pre-alloyed polymer wax and metal have the direct route. So coated and mixed, it's nothing but you are sintering it, whether you are melting it in the like depending upon the application, if you need a metal matrix composite, you can mix the two powders together. If you want to print a very unique alloy, then you can pre-alloy the part in casting or wrought, and then you can make the powder out of it using the atomizer, and then you can print it in LPBF. That can be one way. Or you can mix two different powders using ball milling process, and then you can print it in LPBF process. That can also be done. These are few direct and indirect ways of getting different parts in LPBF.
Excuse me.
Yes.
Yeah. In powder material, the types, ceramic was not given, no?
Here ceramic is not given, but ceramic printing is also there.
Yeah. I think metal powder itself can be called as ceramic.
No. Ceramic are different. Ceramic like silicon carbide.
Yeah. Actually, here if it is a very fine metal powder, it will that will be actually, if it is a metal oxide, then it will be ceramic, no? Like zinc oxide, silicon dioxide.
What you are saying is right. That tungsten carbide and everything, you can call it as a ceramic. But here, the aluminum oxide or other oxides will be called as metal oxides. So they are coming under metal. But
Metal
again,
oxides are ceramics, no?
ceramics, you are right. They are called ceramic as well. But then melting of those ceramics is not possible. So you have to go for the sintering process.
But ceramic is to be given in the slide.
I haven't gone through the video actually. I have just gone through the PPT because this is the topic I'm doing my research on. So that's why I was sharing that ceramic can also be used.
Normally, sintering is meant for ceramics only, mainly.
Yeah, that is
powder
the normal sintering where you apply the pressure and everything. Here,
metal
using laser, you are doing. So application of pressure may or may not be there. Both are possible. But sintering here, it means that you are not melting it. You're just fusing two powder particles together. So for ceramics, melting is little difficult because they burn out very easily. You have to use 30-40 watt power to melt the ceramic to get the part out of it, which is not possible. Melting is very difficult. So sintering is the process people use for ceramic printing in PDF.
Yeah, in conventional powder metallurgy, that is only mainly meant for ceramic materials.
So ceramic sintering was for ceramics, but here the same kind of concept of not melting but fusing things together to get the part is used in PPF called SLS, which is used for both or all the products like ceramic, metal, or polymer. Okay. So you can add the ceramic also in this powder material subsystems because it's not given here. So in coated, as actually you can add the ceramic in the coated as well, because in some cases like tungsten or other metal powders, coating is the only one option how you can print those ceramics or metals, because it's very difficult to melt those metal oxides or ceramics. So coated is one of a kind we use for printing ceramics and metal oxides. So under coated also you can consider the ceramic ones. So it's the description of the subsystems, how it works. It's the EOS int. So the EOS machine, how you can print. There is a powder, video, I believe. Then powder material for indirect route. So this is the binder. So binder jetting is a different kind of additive manufacturing, but in case of PVF also, you can use this type of binder epoxy resin for printing the parts, what you can do is you can mix the binder with the powder particles, and then we can operate the laser in such a way that the laser is melting the binders. So the binder is liquid now or semi-liquid, so they can join all the powder, they can hold all the powders together, and then you can get the sintered part, or you can go for the heat treatment after that. And in the heat treatment, your compaction will be better. So your compaction strength and density will be better. So that is one of a kind. Then the next is the coating thing that I said. See, these are the ceramic particles and these are the coating. So coating can be of binder. Coating can be of other metal as well. For binder, you get the binder in the sample, or you evaporate the binder in the heat treatment process and get the compact strength. But if you apply the metal as a coating, then you can print nice composites, ceramic matrix composites. Or if you do the vice versa, you get the metal matrix composite with the ceramic reinforced. Here we can get the ceramic matrix composite with the metal reinforced.
Here actually it is nylon was given as a binder.
Yeah, here it's given nylon, here it's given epoxy resin.
Polymer.
Yeah. Both are polymer. One is thermoset, one is thermoplastic. So if you see, this is the centering neck. So it's basically the fusion of the atoms first, and then the whole physical powder particles get fused with each other. They don't get melt. So property wise, you get similar to the powder property, like strength, hardness, and everything in the centered part. The center part are more, it's the probability of getting porosity in the center part is more because they are centered together, they are not melted, so there can be porosity in between the powder particles. And the strength wise also, the melted part will give you better strength. Also, very important thing, in PBF we have something called the hatch spacing. The hatch spacing is basically we can have different scan strategy. Okay. So I am drawing a chessboard pattern. That means the laser will first scan this, then it will scan this, then it will scan this, then it will scan this, then this. So they are randomly scanning different squares to scan this whole build area. This is called a scan strategy. Other thing can be to scan this whole area, the laser is scanning like this. Then for this strip, it's scanning like this. Then for this, like it's first going to this direction, then this direction, then this direction, then this direction. So basically it's moving like this and scanning. So this is called a chessboard pattern. This is called a strip pattern. There can be other hexagonal patterns, spiral pattern, then zigzag pattern, no pattern also can be possible. So different scan patterns are there, which is called the scan strategies. Now, as your scan speed is very fast, you have a very nice control or grip over the spooling process in PBF. As your scan speed is very high, your energy density is very high.
Yes.
There, the cooling is also very high in case of PBF parts. So as the cooling is very high, you have a better grip on the control of the process. So on the cooling rate, the main influence of the cooling rate is on the microstructure of the printed. So as your cooling rate is very high, your microstructure wise, the grain size is generally lower or smaller in case of PBF process. As your grain structure is smaller, your hardness is increased, your strength is more. So for PDF parts, the grain size is smaller, the hardness and strength is more because of the high cooling rate. So similarly, if you change the scan patterns, if you change this scan strategies, you can nicely change the whole microstructure of the part. You can change the strength of the part. Even you can print a part like this. In this process, you're printing it with chessboard. In this region, you're printing it with strip. And then again, in this region, you are printing it with chessboard. So this you can do. You will ask, what is the need? So the chessboard and the strip, both the print strategies are different. So their cooling rate and cooling behavior is different. So their microstructural and mechanical properties are also different. So if you want to get a part with different mechanical properties and different microstructural properties at different locations, that you can easily achieve in case of LPBF than any other metal additive manufacturing process. I think according to me, that is the biggest achievement, that is the biggest benefit of using PBFLB over any other metal additive manufacturing process. In case of sintering also, you can move the laser beam in different way so that you can get different strength and property in the different directions. These are the direct route for the subsystem. Then for scanning system, I already told you it's the galvometer based scanning system. So we have the flying optics. So the optics is in the air. Basically, it's moving. The galvometer is moving to get the laser beam on the required position at a very high speed. So this is called the top feeding, where this dispenser moves up and you decode the pour the powder on the bill plate. There can be bottom feeding as well. That means you are feeding the powder from the recorder itself. So your recorder is this thing which is moving, and the recorder is mounted from a powder hopper or powder feeder. So when your recorder is moving, the recorder is having small holes, and from the small holes, the powder is coming. And your powder is getting spread over the bill plate. When it's moving from here to here, the powder is getting spread. Then from here, again, the powder is coming to the recorder is moving, spreading the powder. So it's called the bottom feeding. This can also be done. This is mostly done in case of the electron beam system. For laser system also, the SLM company uses this type of feeding system, whereas the EOS company uses this type of feeding system. Then the recorder it's coming on the manipulator. So for recorder, you can use blade or roller. You can use soft brushes as well. You can use electrostatic gun as well. So that means due to the electrostatic current, the powder particles are getting attracted to the recorder blade, and then when you discharge it, the powders are getting fall down over the bill plate. So that is the electrostatic charge base. This system is mostly beneficial for multi-material printing. For example, just imagine you have a bill plate here, and then your your recorder blade is moving. Your recorder blade is a big roller, and your roller has a differently charged portion at different location, and depending upon that, you have attracted different powders. And when you are rolling and spreading the powder on top of the bill plate, you have printed A, B, B, A, two different powder at two different locations. So you can print multi-material using this concept. Otherwise, the electrostatic one is not that beneficial for single powder because it's more costly. So why to go for that? Roller or blade can to the wall. And slot feeder is nothing but this system, where your feeder or your recorder is having the slot from which the powder is coming. So recorder is spreading the powder and carrying the powder as well. Different systems have different working principle, but it's quite easy, simple. The roller is rolling over the bill plate, spreading. The blade is spreading, and electrostatic, as I said. So now, in case of PVF, as the process is very, very sensitive to all the things, like for laser power, you have to have a very high control and very defined laser power, very high scan speed, because your spot die is very, very small. So as a result of which, we have many other considerations in case of PVF systems. This says this is wrong and this is correct. Because when your reporter blade is coming, we try to avoid as much as lesser perpendicular or lesser line contact possible with the part as much. So we always want to avoid this line contact with the recorder. So this is the line, a straight line of my part, and this is a sharp corner. Both the things should be avoided. My part should not be located like this. My part should be located like this, so that when the recorder has come to this position, it's just touching with this part. When it has come to this position, it's just touching with this sharp end. When it's at this position, it has in contact with this much sharp end. But if you have placed your part like this, when your recorder blade has come to this position, your whole recorder blade is in contact with the whole sharp line of your part. If your recorder blade is a ceramic blade, it can get ruptured. It can get broken as well. If you have a soft brush, then it's better, but still your brush tips may come out. So that's why this tilted position is better. Also, it's not very recommended to have a very sharp corner. It's better if you fillet. Instead of this, if you have a fillet kind of thing in each side, then it's better. A little round. So that we just want to avoid as much possible, as much less sharp contact as possible. Then this position is wrong. So it has a very adjacent parts to each other and also sharp. So one is line contact with the like parallel line contact. It should not be like this. It should be like this. Next, we have 4 parts. So place the part in such a way that there is no other part in these positions. So you see. So if your recorder blade is coming and it gets ruptured because of the sharp edge, then the rest of the part which are in this line can be damaged as well. So if you are optimizing your part, if you are printing a new powder, if you are optimizing for cube printing, it's always preferred to orient the part like this, say 4 part instead of this. If you understand what I'm saying, it's better not to place any part in its axis of each cube, so that if one cube gets damaged, the other can be printed. At least we can stop this part and other cubes can be printed. If you place the cubes like this, and if one cube gets damaged, then the residue of this, because of this, the rupture of the recorder blade can fall down on these parts, and these parts will also get the effect of this part. So I don't want that to happen. I want, if this part is bad, if the parameter for this part is not good, I can stop this part in between the printing, and if I orient the parts instead of this like this, then I can at least print other parts. So that's why it's very important how you are placing the parts on top of the bill plate. Filled atmosphere, open is not even an option. It's not recommended to use open systems. Vacuum is important for EB and inert atmosphere is used for LP, laser beam. Then we have the subsystems. So centering for polymer, galvo scanner, bottom feeding, roller, and open environment is there, but it's not recommended. It can be a very old machine, but these days open environment PVFs are not very common. Then, the bottom feeding with the roller, we can have blade systems as well. So different companies sell different type of systems. Then sintering, but instead of polymer, we can have coated material. Then instead of galvo scanner, we can have flying optics where the scanner based systems basically where the scanner can move. The best combination is for metal, I can say the metal with the melting, with the galvo scanner, with the top feeding or the bottom feeding, but top feeding is better with the blade and with the inert atmosphere. That is the best combination for metal printing. For sintering, polymer printing, again polymer, sintering, galvo scanner, top feeding, blade and inert will be the best combination. But these are the different combinations that are possible, that are available in the market, that is shown here. You can see, you can have a look. Different company names were also mentioned. This is a video of the process. If you see these, you can see, right? These two things. This is the recorder blade. This is the powder bed. This is the powder bed. On top of it, the laser will come. And these two are the sucking system, which is connected outside the machine with the RFS. Through one, the argon is coming. Through one, the fume mix argon is going. So these are connected with the RFS, and RFS is the separate machinery component which will be placed outside the machine. So I think till this much, the lecture has covered about LPBF. If you have any doubt, you can ask me. Otherwise, I can go for the previous year question. Cool. Okay. Then we can start with the previous year question. If you know the answer, try to answer it. Otherwise, I can discuss. In which route of material processing does the laser beam doesn't melt or sinter the powder particles of the desired material on the powder bed itself? So it's the indirect route because it doesn't melt or sinter the powder itself, but we have the coating or we have the binder that we melt or sinter, and eventually your powders get sintered together. Consider the. You have any doubt? No? Consider the following two statements and choose the correct option. Statement 1, in the case of direct route, the laser beam does not melt or sinter the powder particles of the desirable material on the powder bed. Statement 2, in the case of indirect route, no minimal post-processing is required. Both are true. Which of the following type of powder particles is most fitted for indirect route? This is a coated.
Second, both are true.
Actually, I think that the first one is not true. The laser beam does not melt or sinter the particle of the desert. This is not true because the direct route is where the laser beam directly melts or sinter.
Yeah, then it
should
is
be
not
only
true.
2 is true.
Only 2 is true. But why?
Yeah, I don't know why they have Actually,
of
they have
indirect,
given the answers. It's not my answer.
of
So
indirect route, no minimal post processing is required. Actually, both are false. I
both
think
are false because in case of indirect also you have to go
indirect
for at
route,
least heat treatment.
indirect route, we should go for post processing.
Yes, it should
Indirect
be
means
both are false.
both
I
are
don't know.
false.
There can be some misprinting as well from their side or from my side, but it
But
should be both are false.
from our side, what we have to can take? But we want marks, no?
Yeah, but it's like you cannot know that what they have done something wrong or right, but the answer should be both are false with no doubt.
Third question, yeah.
It's which of
Following,
the following type of powder particle is most fitted for indirect route? It's the coated one.
yeah.
Select the incorrect statement made in the context of green parts obtained from indirect selective laser sintering. The green parts are nearly anisotropic. In any case, the parts are little bit anisotropic in case of PBF. We try to make them isotropic, but here it says it's incorrect. But in case of normal PBF systems, the parts are, we try to achieve it isotropic, but it's always not true. The parts are towards isotropic, but not fully isotropic.
Green
So
parts
in case
are
of,
density, yeah.
we try
Remaining
to
are
make
correct.
it, yeah. Consider the following statement made in the context of scanning system used in uh, scanning system. Where is it? Used in powder bed based additive manufacturing system and choose the correct option. Statement 1, beam correction in active optics is generally achieved by dynamic focusing. F theta lenses are very effective while scanning a very large working area. So no, F theta lenses are not very effective if you are scanning a whole large area because it's used to make the laser focus at a very given tiny range of theta angle, which is directly proportional to the area of the billprint.
Yeah, first one is it flying
Beam
optics?
correction in active optics is generally achieved by dynamic focusing module. Yes.
That
That,
is equivalent to flying optics. Statement
yeah,
one.
yeah. That is the dynamic
Dynamic,
focusing module.
dynamic focusing means flying optics.
Yeah, the active optics, beam correction in active optics is the flying optics, and achieved by dynamic focusing module means we have the multiple set of lenses to
Yeah.
which you can focus at a different region. So that is the scanning system.
Second one is
Call it
galvanometer.
scanning. Yeah, second one is false.
Galvanometer.
Galvometer.
It
But
cannot
again,
cover.
galvometer also has a range because before galvometer we have placed the F theta lenses. So in any case, the working area is defined by both F theta lens and galvometer. Galvometer is there to to speed up the process, but F theta lens defines the area.
But F theta lens are part of galvanometer.
No, both are different modules. Both are different things.
No.
We integrate both together.
But the entire setup we are calling it as galvanometer. But in that the lenses.
Entire setup actually we are calling it as galvometer, but the galvo scanner and F theta lens are both different things. So when you are using galvo scanner, you can use F theta lens or you can use telecentric lens as well. In PBF systems, mostly we use F theta lens. That's why it's kind of a unsaid rule that we are using F theta lens and galvo scanner, which we are calling it as a galvometer, but it's not true that galvometer means F theta lens only.
No. They are not equivalent. But F theta lens may be a part of galvanometer.
Yes,
Maybe.
here the F theta lens is a part of galvometer.
That's what is in the statement.
Yeah.
Phase galvanometer doesn't include F theta lens.
Yeah. Okay, next question. Consider the following two statements made in the context of recoating system for powder bed based additive manufacturing and choose the correct option. Counter rotating type roller is used for achieving good powder flowability. Forward rotating type roller is used for powder compaction. Okay. You can even note down this small informations that forward rotating type roller is used for powder compaction and counter rotating type is good for powder flowability. In which of the following scan system entire optics moves in the XY table? Is the flying optics, where the entire system moves. Otherwise, in galvometer, it's fixed. Even in mask phase also, it's fixed. Compaction of powder layer will be higher in which of the following sweaty system? Is the, as we said in the first thing, is the forward rotating type roller. In which type of recoater is used for preparing uniform powder layer of very high accuracy? I think it's the recoater with ceramic blade. The whole recoater is not made of ceramic, but the blade is made of ceramic.
Very high.
Because it's giving us a kind of rigidity in layering the powder. So that's why it gives us very uniform powder distribution. In the context of hybrid recoating system in powder-based aim, the doctor blade is used to spread the powder, followed by vibrating the counter-rotating roller on a large area to compact the spread powder layer. Okay.
So almost the questions are there in the assignment, same questions.
Okay, same questions are given.
Almost.
Okay. Consider the following statements made in the context of recoating system bed powder based. So powder reservoir travels in the recoating direction to spread the powder layer. Electrostatic method is commonly used for powder particles of polymer. Polymer cannot be used for electrostatic. It's already false because it's not charged state.
To spread a powder layer on the powder.
Powder reservoir means the kind of a recoater which is connected to the powder hopper kind of. Through the recoater, the powder is coming. So that system.
Only one is true.
Yes. And anyway, the polymer cannot be electrostatically charged. So electrostatic method cannot be used.
It's not conductive.
An inert environment type built atmosphere in powder bed aim is generally preferable for processing of metals to avoid oxidation, to increase the efficiency of the process, to protect optics from fumes. All of the above. Next, in the context of built atmosphere, the statement 1 is for processing the polymer powder, an open environment is generally preferred. Statement 2 is vacuum type environment minimize the convection heat transfer as the result or the temperature of the bed will be uniform temperature. Both are true. So vacuum is achieved because of the electron beam, but as vacuum is there, it minimizes the convection heat transfer. As a result, the temperature of the bed will be uniform at temperature. And for processing of polymer, we have seen various companies are going for the open environment. Because also there is one reason, the polymer, in case of polymer, the fumes will be also there. If you're going for sintering, it's lesser. If you're going for melting, it's higher. Anyway, the polymer is used mostly for sintering, not melting. But if you're going for melting, the fume will be very high.
But anyhow, it is open environment, no? Open environment
Yeah, it's
means
open. So see, if you,
there is no,
for
if it is a closed
polymer,
environment,
there is
yeah.
no chance of oxidation. Or your fumes are also lesser in case of sintering. So why to go for an inert gas atmosphere just to higher the cost of the machine?
Only with metals we have problem.
Yeah,
Oxidation.
so if open environment can be worked, then it's preferable because it's minimizing the cost. So for polymer, it's okay. Passive optics in the powder bed aim uses dash for beam correction. Is the F theta. Passive optics means the fixed things. That is not the dynamics one. So that is the galvometer one. So for beam correction also, F theta lenses are doing that.
Active optics in the sense, is it flying optics?
The flying optics, yes, where dynamic focusing modules are used. Because there are the scanners also will be there which can move up and down to correct the beam. But here F theta lenses are doing that.
So like galvanometer.
Yeah, galvometer. Consider the following statement. One is parts in SLM can warp due to high thermal gradient. Support structure do not restrict part warpage. They are used for supporting overhang features only. The support structure also restrict the part warpage. So they are not only used for supporting the overhanging. Supports are also used for dissipating the heat so that your warpage will not be there. Only one is true.
One is true.
Consider the following statement. The substrate should form a brittle interface with the first layer of the part. The substrate should form a bond with the first layer of the part. So if the substrate is forming a brittle interface, then there will be high chances of the warping. So only 2 is true. It should get properly bonded and the dilution should be proper with the substrate.
First layer of the part. Substrate should form bond.
First.
Actually, substrate should form a brittle interface with first layer of the part.
No, it should not face any brittle interface.
Form a bond with the first layer.
Yes. And also, importantly, remember, when the scanning happens, in case of melting, 2 to 3 previously bonded layer also get remelted because of the high heat and energy density. While
Afterwards,
printing.
substrate should be separated, no? Afterward,
Yes.
at the end.
We will cut the part from the substrate.
Substrate is like a sacrificial material.
Substrate, the substrate will be reused again and again, but you can see the first few layers are sacrificial because when you're cutting the part from the substrate, first few layers get cut as well. So those are the sacrificial, like the support structures are sacrificial.
How entire sacrificial in the sense, entire substrate gets spoiled, no? While removing.
No, so after removing, the substrates are mostly of 35-25 mm height. So it's very thick. So after cutting the part, we grind the substrate again to reuse it again.
But the thickness will be reduced, no? Or what? I don't know.
Thickness will be reduced by few micron only, so it doesn't matter. When you cut the part, if
how can we cut that? Can you explain?
So if you have the substrate here, and if you have the part here, we cut the part from here. We don't sacrifice the substrate. We sacrifice few portion of the part. So this much, after cutting the part from the substrate will look like this. So then if you grind the substrate, only few micron of the substrate is gone. So there is one process called wire cut EDM process. Have you heard of it?
Yeah, so wire is responsible for cutting the material.
Yes, wire EDM is the most effective, efficient machining process for cutting parts from substrate so that most of the part is useful. The sacrificial portion is very less. Otherwise, the band saw or automatic hacksaws can be used as well.
So
There,
sacrificial
the
material
wastage is little higher.
from the part material only, the
Yeah, it cuts from the part material only. We don't cut the bill plate.
built material. Okay, thank you. So wire
Then
EDM is
which
not
of the yes,
okay. Continue.
yes, wire EDM. Sorry.
Normally used for
Yes,
cutting
yes,
the material from the
yes.
substrate. Okay, okay.
People use band saw and automatic hacksaw as well, but there the wastage is little higher. But you can use it. Which of the following is not a joining mechanism in case of powder bed AM? Photopolymerization, otherwise sintering, liquid sintering and melting are the process involved in PBF. Which of the joining mechanism for this applies heat to increase the temperature of the substrate powder above the melting point? It's the melting. I think there was a sound.
So 19. Can you repeat?
Yes. So melting is the process in which we apply a lot of heat to increase the structural powder. The temperature of we increase the temperature of the build plate as well, and we increase the temperature more than the melting point of the powder. The density of the part produced will be maximum in case of with joining. So it's the melting process. Because you are completely melting the powder, so compaction and density is greater. Next is the which of the things are better. So orientation 2 and orientation 4 are the better way to orient the part to avoid any breakage in the recorder, harm in the recorder as well as in your part. So these are the common, there are few common questions. So I can quickly go through. These are the 2 years back questions, basically. So I think these questions are almost similar. Anyway, I will share this PPT with you. You can go through the other questions as well. Right now, we can go for the Mentimeter. Okay. We can start with the regular Mentimeter one. You can scan this QR. Yes. So you can scan this QR, all of you, and join the test with your phone. Let me know when you have joined. All of you can scan the QR. Shok and other whoever has joined. It's a fun game. So, okay, so I'm starting the questions. Here is your first question. Of the following is true about powder utilization.
DED has a higher efficiency.
No, powder, if you utilization, yes, DD is higher, but the DD, I mean, the process rate is higher in DD. But if you talk about powder utilization, then in DD there are a lot of wastes because there is DD is a powder blown process. So the powder is coming, it's blown away. So a lot of powders will be here and there near the deposition zone, which you cannot reuse. But in case of PBF, lot of powder, way more number of or amount of powder will be there, which you are not printing but spreading. But after the printing, you can reuse the powder after sieving. So powder utilization efficiency is very high for PBF. Although you are using lot of powder to spread for each layer, whether you're printing or not printing, but you can reuse the powder. In case of DD, you cannot reuse the powder because it's oxide and it's gone, it's contaminated. So that's why DD
In,
has a
in,
higher deposition rate.
in SLA also, where you have vat containing a lot of liquid. So the
Yes.
remaining liquid we are using.
Yes. We are using the remaining similarly after kind of sieving also. There also we sieve it. The liquid also we sieve and then put back. There can be some melted solidified parts mixed with the liquid. So, which AIM process is better suited for repair of large components? This should be tick marked correctly. So for uh, first
We
of
have
all,
seen, no?
repair is with cladding like DD. Then large component is also related to DD. Okay. Repair is very difficult in PTF and we will not go for PTF for any repair. And large component is also related to the DD because DD is open environment. You can print as much as you want. But in case of PBF, it's the closed chamber. The F theta lens is defining your build volume. So that's why it's better for D. Then your third question. It is just the vice versa, like the opposite thing. So in case of PBF, you can get a very high resolution, very less wall thickness. But in DD is for higher deposition. One fundamental thing you have to remember, DD is for higher, larger component, repairing, higher deposition rate, printing high volume material or high volume parts.
But PPF is for small intrinsic parts, internal features, very small wall thickness and higher resolution. Okay, it can be very like difficult to remember, but at the beginning, but just remember the process, how it's going on. Then you'll understand. Process generally achieves high building rate. So here is the higher building rate. This should be the DD. Yes. Next question. Powder bed and reporting mechanism. It's a so very easy question. The PVF. Next. Yes. Because you just take away the powder from the collector, you put it in the sieve, and your powder is sieved. Although the process is very hectic and time consuming, but still it's very straightforward. Hybrid manufacturing more easily किसमें हो सकता है? It's the DED is the only one process where it can be done. Powder bed में तो बहुत ही मुश्किल है, नहीं हो सकता. Because it's a control atmosphere. We cannot integrate lot of machinery parts, big machinery parts inside the. Next. Which process generally shows lower resistance stress for larger components? So residual stress is coming from the high cooling rate, because residual stress is like high temperature gradient, high cooling rate, more residual stress. In PBF, the cooling rate is much higher, so the residual stress is much higher. That's why DD will give us lower residual stress. These questions just will kind of increase your knowledge in that particular topic, I believe. better surface finish तो we can get from PBF, because ज़्यादा से ज़्यादा क्या होगा, we can have the unfused powder particles in the wall that we can get rid of in any ultrasonically cleaning or sandblasting. And the surface roughness that we get in PBF is generally around few micron, like 2 to 3, 4, 5 micron, maximum 3 micron, I think. But in case of DD, we do not get a good surface finish because we get bigger surface undulations. We get the waviness. We don't get roughness. In DD, we call it as waviness. Waviness means the waviness is in millimeter. So the surface finishing is in millimeter, the resolution of the surface. So that means the complete milling process or kind of surface coarse grinding process is needed. For PVF, it's not that hard to finish the surface, but in PD, you have to basically cut the surface away, the top surfaces. So the surface finish is more in case of PV. Next question.
So machining done on that DED part will not be
ED
considered in this
parts,
case.
yes. Yes. Yes, PBF is higher resolution, low build rate, but DD is low resolution but higher build rate. See, बस याद रखना है. Next question. Which of the following correctly distinguishes SLS from SLM? One is selective laser sintering, one is selective laser melting. As the name suggests, you can get the idea out of it. Yes, so SLM fully melts, SLS only sinter. Next. Which process is more commonly used for polymer and which for metal? Yes, SLS for polymer, SLM for metal, and also powder bed fusion. Some people, at the beginning, I have seen the other students to mix up with DED. So DED can be worked with powder and wire both, but powder bed fusion, its name suggests that it only can be worked with powders, not with wires, because you have to spread the thing. So you cannot spread the wire. So it's only the wire thing, powder thing. But DED can be worked with metal and wire both. But DED cannot be worked with polymer, but PBF can be worked with polymer as well. Regarding mechanical properties of final parts, which statement is correct? I have 30 seconds for this. The SLM parts typically have higher density and strength than SLS part, because SLS will give us porosity because it's just the compaction out of the laser. Sometimes we are not even applying any pressure onto it. So it's just the binding materials are getting melted or the coating are getting melted, not melted, like sintering the powders together by melting themselves, or the powder are getting fused together. So at the necking also there can be porosity. So the chances of porosity is way higher in SLS than SLM, because in SLM we are properly melting all the powders. And also, as I said, for SLM, when we melt one layer, previously deposited 2 to 3 layers get remelted. So the chances of getting porosity also minimizes by this. That's why the residual stress is also higher. Next question. So powder typically delivered to the build plate after each layer is fused. It's mainly by the roller or the coating blade across the build plate. Uniformity of powder layer spreading in PDF. It's the ricotta type and the powder flowability. The flowability is achieved by choosing the spherical powders also. Typical layer thickness, I have mentioned this in the during today's session. The layer thickness of the process.
10 microns, 2200.
It's 2200 micrometers.
I guess. Directing the laser beam. Power. Is it? It's a galvanometer.
Directing the laser beam across the powder bed is the galvanometer mirrors. Question 18.
Gaussian laser beam.
Gaussian laser beam profile often used in LPD. It avoids the keyhole formation at high power. So Gaussian beam, the laser intensity profile is not actually related to the keyhole formation or conduction mode. It's related to the power which you are giving. Yes, Gaussian beam will have higher probability than top hat profile to have keyhole if you have higher power. But the keyhole formation is mostly related to the higher power if you are giving way more power than the required one. But the Gaussian beam is concentrates maximum energy at the center, adding deep penetration. And also beam means single mode Gaussian beam. So kind of you're utilizing all the power that you're giving in the input. So higher utilization of the power also. So less wastage, you can say. Next, second last question.
Power.
Often offer high peak quality, stability, because fiber laser can give me very easily single mode Gaussian beam, efficient deliveries via fiber, less wastage, over wastage.
Madam, here fiber in the sense, is it optical fiber?
Optical fiber.
Yeah, it passes, it comes through that fiber. Okay.
Yes. No, fiber laser means the source is also fiber and it will also be delivered using optical fibers. So the last question. Which component in the LPBF scanning system is primarily used to rapid steer the laser across the powder bed without but high precision? If it answer is fast.
Precision. Colorimeter.
Yes. To steer it fast, only the galvo scanner. Okay. Okay. So these are the all things I was having for this week. If you have any doubt, you can ask me anytime. You can mail me anytime. Also, I have an announcement. So this was my second last class, week 11. Week 12 is gonna be the last class, which is on 10th October. But I have decided to take an extra class on 11th October, Saturday, 1 hour extra class, 6 to 7 p.m. If you have any doubt for the final exam, you can let me know on that day. I can prepare some Mentimeter to revise the whole session till date. We can discuss on some topics. It's better if you tell me beforehand which topic I have to discuss. Then I can also go through a few things about that. Otherwise, I'll go through the general topics of additive manufacturing, all the type of classification and everything. So that is on 11th October from 6 to 7 p.m. You'll have the official mail of that as well.
Yeah, one doubt I have.
Yes.
Shall I ask now? So
Yeah,
that is
you can
regarding
ask.
the file formats. Actually, the second phase is after getting the CAD file, we are converting into STL.
Yes.
But in STL, actually, we are getting some errors. That is why some correction we are doing to the STL. So actually, that I have read in the textbook. But what is the status right now? Still, those errors are like that only, or any modification is
No, it's
made?
if you're making the CAD files, then you can convert it to 3DMF also. There is new file format called additive manufacturing, 3MF or 3DMF. Can
Yeah, that
search.
recently that is a development.
Yeah, recently added. Yeah, that is also compatible to most of the softwares. I don't know if you are going for FDM. I think for Curato it is easily accessible. But in other systems, we are still using STL only. I am still using STL only. I am converting it to STL.
A lot of repair work will be there now. We are finding some gaps or
Yeah,
we
so for repair work, actually correcting the STL is quite difficult. So you have to have large computational power in your system, and you have to have other softwares also. Like I use SolidWorks, but SolidWorks is not good for doing this repair thing in the reverse engineered parts CAD models, because after reverse engineer you get the STL, and correcting the parts in the STL is quite difficult.
it's better if you can convert it to the SLD or CATIA file and then rectify it there, then convert it into STL. There is no other way actually. You have to put manual labor into that.
No, but actually in that book we read that STL file itself they are doing repair because there is a process like in a kind of algorithm
Yeah,
where
I
we are
know
separate.
STL file repair is also there, but the normal SolidWorks or this CAD software cannot do that. The software name I forgot. I don't remember the software exactly, which you
In
can
STL
use for repairing this
it
STL.
is out of the vertices and the edges. STL
Okay.
where whether that edge is repeating or not. So that kind of thing will be there like an algorithm because
Okay.
every edge is common for two triangles because two triangular facets that actually that kind of verification is to be done whether the edge is common for two facets. If it is not common, then there is an error. Like we have to verify the entire STL model that is made out of triangular facets, and then that way we have to make it repair. So that process is there for STL repair. Okay.
But I think I cannot help you in repairing the STL because I have tried it once few years back, but it was quite difficult. My work doesn't involve that, so I never have installed any other apps to do that. I'm not
theory only.
very used to it.
And
Sorry?
theoretically, that is the procedure. I'm not asking you to do the practically.
Yeah, I understand your problem. But theoretically, yes, the facet should be
But
one line should be shared by two facets.
yeah. I think because a lot of research is going on, no? Whether that kind of things might be sorted out and maybe that kind of doing repair might be eliminated and a better format might have come. Like that, I'm thinking.
Okay, but I only know about STL and the 3D MF, that new format.
Meanwhile, you inquire and because in this additive manufacturing, some of the time will be wasted and because in correcting the STL file format.
Yeah, I know.
Whether any changes or any updations were made or developed so that the time we are spending earlier for the elimination of errors was now it is minimized like that kind of thing I need.
Okay, I can search about it. I can ask people.
Yeah.
And can I know which process you are using to print?
No, it is theoretically I'm asking because it is common.
Okay,
it
only
is common.
theoretically.
Whatever type of procedure, STL repair is common before going for building. In that process, because the STL repair is taking time, so that is why we need a better file or maybe rectification of this STL file so that only minimum errors may come.
Okay.
That kind of work.
I'll search about it. I can ask people who are working on this.
Thank you.
Okay. Thank you for attending. Happy Dasera again. We'll meet in the next.
Same to you. Thank you.